Okay, so now that we've proven the Pythagorean theorem a couple of times, we're going to explore some of its properties. We know that if we have a right triangle with side lengths a, b, and c, that we can take a squared, add it to b squared, and we will get c squared. Okay? Now that looks like a very nice relationship, but there's no reason to assume that it necessarily can take on very nice values. It would be really, really cool if this had integer solutions, where a, b, and c are all whole numbers, positive preferably. I guess it wouldn't matter if they were negative because we're squaring, so everything becomes positive anyway. But in fact, there are integer solutions to this. There's one for every odd number, in fact, so there are infinitely many, and I'll be happy to prove that there are in fact infinitely many. But there are 5, technically 6, where the starting number, a, is less than 10, so I'm just going to give you those, and I recommend that you commit these to memory. So the most famous one is 3, 4, 5. Right? So if you take 3 and you square it, you get 9. If you take 4 and you square it, you get 16. 9 plus 16 is 25, which is 5 squared. In other words, 3 squared plus 4 squared equals 5 squared. So it really does work. If you take a line of this length, and this length, and put them together into a polygon, you will get a right triangle with side lengths 3, 4, and 5. It will happen. The next one that has 5 is 5, 12, 13. And then there's 7, 24, 25, 8, 15, 17, and 9, 40, and 41. So that's every one where the first number is less than 10. Technically, there is this one. Right? 1 squared is 1 plus 0 squared being 0. 1 plus 0 is 1, which is 1 squared. So this is technically a Pythagorean triplet as well. That should hint that we will eventually be seeing what trig functions give these values, by the way, which seems a little weird. But these are all Pythagorean triplets. Anytime that 3 integers come together in this way, it is a Pythagorean triplet. Notice that all of these are triplets of coprime numbers. If you look at any of these, there's no pair of numbers in any triplet that shares factors. 7 and 24 are coprime, 7 and 25 are coprime, 24 and 25 are coprime. These are called primitive triplets. If I were to take a 3, 4, 5 triangle and scale it up by a factor of 2, scale everything up by a factor of 2 and double all the sides, I would get a 6, 8, 10 triangle, right? But these numbers all share the factor of 2, so I could divide it out and get back to a more primitive one, namely 3, 4, 5. But this still makes a perfectly valid right triangle. It's just a scaled up version of this. The Pythagorean triplets that you tend to memorize are ones that are not reducible, right? They have only coprime numbers. Because any pair of numbers inside of a triplet are coprime and therefore don't share any factors, you can never have 2 even numbers in a reduced triplet, because if you did, then they would share a factor of 2. So 2 out of every 3 numbers in a Pythagorean triplet is always odd, because if there were 2 even numbers, like I said, they would have a factor of 2. So let's see if we can come up with a way to actually generate these. Right? I just gave you a list. You can numerically test any of these, that the first number squared plus the second number squared is definitely the third number squared, but how did I come up with these? Like, where did they actually come from? So let's investigate that. Okay, so how are we actually going to figure out how to generate these Pythagorean triplets? Well, we need a way to come up with an equation where the left side is something squared plus something squared, but we need those 3 terms to all be based on one collection of numbers that we choose, right? We don't actually know the relationships between A, B, and C when it comes to coming up with a triplet, so we need to find a way such that A, B, and C are all in terms of the same 1, 2, or 3 numbers that we want to pick to generate these triplets. So let's investigate something that we did earlier in the topic of the Pythagorean theorem, which is look at binomials being squared. If you recall, if you square a minus b, you get, similarly to squaring a plus b, you end up with a squared minus 2ab plus b squared, right? But take a look at this. This is a square, so if I can find a square to add to this and get another square, that would be really convenient. And this is almost what we need. Take a look. So I'm going to take this thing, and I'm going to add a couple of these. So this is minus 2ab. I'm going to add 4ab so that this becomes plus 2ab, because minus 2ab plus 4ab is going to give us plus 2ab. So if I add 4ab to both sides, so we end up with a minus b squared plus 4ab equals a squared minus 2ab plus 4ab plus b squared, right? That's what that is. But take a look what happens. These combine to give us plus 2ab. But look what we've ended up at. We've ended up at a plus b squared. Now that's really good. We've gotten a square to which we've added a term and gotten another perfect square. The only problem is we do not have the fact that 4ab is a perfect square. The only way we would know that 4ab is a perfect square is if ab is a perfect square. 4 is a perfect square, it's 2 times 2. But we need to know that this product of numbers here is also a perfect square. So we need to be a little more clever. What if a itself was the square of a number? And the same thing with b. Then we could guarantee it, right? If we could somehow make it known that a is a perfect square and b is a perfect square, then 4 times a times b would itself be a perfect square. So can we think of a way to do that? Well, sure. Let's just let a equal, pick a letter, k squared, or, yeah, sure, k squared, and we'll let b equal t squared, right? Two new variables. A is k squared and b is t squared. So let's see what that does to our math when we insert these new substitutions. So we've said let a equal k squared and b equal t squared, right? So what is that going to get us? Well, we started with a minus b quantity squared, so if we replace a with k squared and b with t squared, we start here. So k squared minus t squared squared, right? Remember, this is a and this is b, and we started with a minus b squared. So this is what we've got now. But now we get to FOIL this out in the exact same way that we would do if this were just a and b. We have to square the first term, which gives us k to the fourth. And we have to subtract 2 times the product of these two things. So minus 2 times k squared times t squared, right? And we have to add the square of this term, so plus t to the fourth, right? Cool. So we've got this relationship now. When we add 4 of these things, we're going to be adding a perfect square. So look, if we just add 4k squared t squared to both sides, right? This is a perfect square. It is 2kt all squared, right? Because 2 squared is 4, k squared is k squared, and t squared is t squared. So this is the same as 2 times k times t squared. We are taking a perfect square and adding to it a perfect square, just like the left-hand side of the Pythagorean theorem. But now look what happens. Negative 2k squared t squared plus 4k squared t squared gives us positive 2k squared t squared. So we end up with k to the fourth plus 2k squared t squared plus t to the fourth. And this is our perfect square, because this is exactly the same as this, but with a plus. So this is just this, but with a plus. This becomes a plus, and this is equal to k squared plus t squared all squared. So we have done exactly what we wanted to do. We took a perfect square, added to it another perfect square, and obtained a third perfect square. The important bit is that all 3 of these terms are in terms of the same collection of numbers. It could have been 1 number, could have been 70 numbers. The point is that It's some finite amount of numbers that determines the value of all three of these things, and yet they are all squares. So all we have to do is pick our values of k and t, and that will generate a Pythagorean triplet if k and t are integers. Now remember what I said about primitive triplets before. Every single triplet that you have been told are like the basic ones always have no factors that are common between them. One of the necessary criteria of that is that 2 out of the 3 numbers in a triplet are always odd, because again, if 2 were even, then they would share a factor of 2 and therefore would not be coprime. So to guarantee that that doesn't happen, we need to make sure that not both k and t are even, because if they are, then this will be even because it's a multiple of 2, and an even number plus an even number is even, an even number minus an even number is even. So then when we get even, 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 and then that wouldn't be a primitive triplet. It would still be a perfectly valid Pythagorean triplet, but it wouldn't be one of the simple ones. So if we want to get 3, 4, 5, all we need to do is pick k and t that are going to be the ones that satisfy that relationship, and this product will determine what this is going to be. By the way, this number, this one will always have to be the even one, because we're multiplying by 2. No matter what k and t are, you could pick an even and an odd or 2 odds. This will always be the even term in the triplet. And notice, it's this square plus this square equals this square, and this is not on the other side of the equation. So the even number is never going to be the hypotenuse. So let's write this new expression up top, and then we'll see if we can generate those triplets that I mentioned. We have k squared minus t squared all squared plus 2 times k times t all squared is equal to k squared plus t squared all squared. And this is true for any k and any t, and creates a Pythagorean triplet. Notice, it's something squared plus something squared equals a third thing squared, which is exactly what the Pythagorean theorem says. Now, since this has to be the even number, and I want to generate the 3, 4, 5 right triangle, what do k and t have to be? Well, if this is going to be the even term, it has to equal 4, if we want to build a 3, 4, 5 right triangle. So if I want 2 times k times t to be a product of integers that gives me 4, either k or t has to be 2, and then the other one has to be 1. It doesn't matter which one we pick. I'm just going to choose k to be 2 and t to be 1. So if k is 2 and t is 1, then we have 2 squared minus 1 squared all squared plus 2 times 1 squared equals 2 squared plus 1 squared squared. And let's analyze this. 2 squared is 4 minus 1 squared, which is 1, gives us 3, and this says 3 squared. 2 times 1 is 4, and that's 4 squared, so plus 4 squared, and 2 squared plus 1 squared is the same as 4 plus 1, which is 5, so this says 5 squared. And if you look at that, we've got our triplet, right? And so you can use this formula right here, given particular choices of k and t, to generate all of those triplets that I mentioned before. I'm only just doing this one to show you the proof of concept, but the others can be generated in an equivalent way. So now that we figured out a way to generate the triplets, that's really cool, because now we can come up with any ones that we want. So maybe keep this formula in the back of your mind. It's not that big of a deal with regard to the Pythagorean theorem, though. What really matters is remembering which ones are the triplets, because that'll allow you to solve algebra and geometry problems relating to right triangles pretty easily. And now it's time to move on to what's normally known as special right triangles.